Good morning. Welcome to High School Algebra I. For those of you tuning in for the first time, my name is David Dye. I am currently in my third year of teaching and second year at Algebra I High School. This semester I am teaching algebraic connections and discrete math. The last couple of weeks we've focused our attention a lot on quadratic functions in critical standard 1 and 2. So as we transition to critical standard number 3, we're going to focus our attention more on exponents and their properties, and then how we can use those properties to make sense of polynomials and then their operations. So the way I want to address this is kind of thinking back to the questions that I posed last week at the end of last week's lesson. Focusing our attention around the idea of what is the meaning of an exponent, and then thinking about, are there any relationships that exist when we're using exponents, and then lastly, how is the number 1 related in terms of how we understand these exponent relationships. So my learning goal today is for you to be able to identify these patterns and relationships and then generalize the relationships so that we can approach and solve novel problems. Now, my agenda for accomplishing this, we're going to revisit some prior knowledge. I'm going to give a task called the dream job salary task. And then once we address that task, we're going to look for patterns with the exponential relationships, and then we'll summarize the lesson and then look ahead to our final week next week. So, the dream job salary. The situation here is that you're being offered a 30-day trial job at your dream job. Now, the owner of this company is a little unusual and offers really non-traditional pay. And so he's giving you 2 options to choose from in terms of how you want to receive your money over the course of the 30-day period. So option 1 is that you are going to be paid $60,000 each day. To put that into perspective, over the course of a year, I make less than that. So you would be making $60,000 each day for the course of this 30-day trial period at this job. The second option is that you would get paid 1 penny on the first day, 2 pennies on the second day, 4 pennies on the third, and then 8 pennies on the fourth day, and then so on for the course of the 30 days. So you're asked to choose between these 2 pay options, and you want to think which of the 2 pay options is going to give you the most amount of money at the end of the 30 days. All right, so as you're thinking about which option you're going to choose, I'm going to kind of show you how much money you would be taking in on a daily basis, on day 1 all the way through to day 30. And then we're going to see which of the 2 options would be the best. So looking at the first set of 10 days, notice here that in option 1, we've got $60,000 each and every single day. That is consistent, that's unchanging. In option 2, as I stated earlier, you start with 1 penny, you get 2 on the second day, 4 on the third, 8 on the fourth, 16 on the fifth, and so on. So by the end of the 10 days, option 1, on the 10th day, you're still earning $60,000, whereas in option 2, you're making a grand total of $5.12 on that 10th day. When we look at the next set of 10 days, again, option 1 holds steady at $60,000 each day, and I'm looking at option 2, and it doesn't occur until day 15, but on day 15, you're now into the triple digits in terms of the amount of money earned. You're earning $163 on that day, and then by day 20, you're earning $5,200. So $5,200 on day 20, whereas in option 1, you're still earning $60,000. And again, you want to keep in mind which of the 2 pay options you're going to choose so that you have the most money at the end of the 30 days. Let's take a look at the last 10. So by day 23, the second option is now paying you $41,900, and then again, option 1 is still holding steady at $60,000. By day 24, option 2 is going to pay you $83,000. By day 25, you're looking at $167,000, and then by day 28, you're looking at $1.3 million on a single day, all from doubling with a single penny. So if you chose option 1 at the very start of this, over the course of the 30 days, you would take in $1.8 million. But think about where that total kind of stands relative to option 2. You'd be making 1.3 on a single day in option 2. At the end of the 30 days, option 2 is going to pay you $10.7 million. So what kind of patterns are you noticing as we think about this pay structure, where you're either getting paid $60,000 every single day, or your pay is getting doubled from a single penny over the course of 30 days, and that total gives you that 10 million. So I want to contrast and kind of compare what these two types of relationships are that we're looking at. In the first one, where your pay option is $60,000 each day, we're looking at something that is linear. If I were to graph those $60,000, we would end up with a straight line. And so we're starting with some kind of initial value, and then what's happening is that we're adding on a constant rate over a constant interval. In this particular case, we're starting with $0, and I'm adding on $60,000 each day. And then over the course of the 30 days, I could represent my pay as starting with $0, and then I've got that $60,000 each day times the 30 days to give us the 1.8 million. Now, the difference between this linear relationship and the exponential one that option 2 offers is that similarly, you're starting with some kind of initial value, starting somewhere. But the difference here is that instead of adding on a constant rate, we're going to multiply by a constant rate. So we're doubling. In this case, I'm starting with that 1 penny. I'm doubling the amount of pennies that I have from day 1 to day 2. So now I have 2 pennies, and then 4 pennies, and then 8. And I could represent this as having that 1 penny times 2, because I'm doubling, and I'm doubling over the course of 30 days. So my exponent there is going to be 30. And that gives us this value of 10.7 million. So that first question that I posed in terms of reflecting back on last week, I asked, what is the meaning of an exponent? And here, I want you to understand that an exponent tells us how many times we're multiplying some kind of initial value by a base or by a certain rate. So this 30 tells me I'm going to multiply that 1 penny by 2 over the course of 30 days. So that exponent is going to tell me how many times I'm changing my initial value and at what rate that change is going to occur. So now I want us to kind of take that definition and think about this particular expression. What do you notice in this problem that I'm posing? And you might say that you see a lot of 2s, you see a lot of 3s, a couple 5s, a 4, but the location is important also, right? So these 2s and these 3s here are the base of our expression. These 2s and these 3s in the upper right are the exponents. And my question to you is, what would your strategy be for simplifying this particular expression? How would you figure out what that is equal to? Now you might work it out by hand, evaluate 3 to the 5th power, 2 to the 3rd power, and work it out by hand in order to find a single answer. Some of you might say, ooh, I've got a calculator, so I'm going to use technology, type that in and find an answer. But what if I told you that this answer is 1? How does this unruly expression simplify to 1? And is there a more efficient way that we can simplify this without having to use technology or evaluating every single part by hand? And that's going to be what we're going to explore in terms of looking for patterns and relationships to help us answer this question. So as we look for patterns and relationships, I want to make a note that when we're talking about exponential expressions like 5 cubed or 8 squared, that the initial value we're starting with is 1. In our dream job salary task, the initial value, what we started with, was 1 penny. But when we're not looking at something that is contextualized and something that is as simple as these expressions, our initial value is going to be 1. And so when we're talking about 5 to the 3rd power, what we're saying is 1 times 5 3 times to give us a total of 125. And when we're talking about 8 squared, that's 1 times 8 2 times to give us a value of 64. Now, when we're looking at this table, what I'm showing you on the left-hand side is an expression. In this case, 10 squared times 10 to the 3rd power. The expanded form of what we're seeing in this expression. So I've got 1 times 10 2 times, and then I'm going to multiply that times 10 another 3 times, which if I rewrite as a single exponent, can be written as 10 to the 5th power. So what kind of patterns do you notice between the expression that I'm giving you here on the left-hand side and the single exponent form that I'm showing you on the right? What kind of connections exist between this form and then what we see on the left-hand side? And before I answer that question, I want to go through a couple more examples just to see if you can kind of pick them on these patterns. If I'm looking at 10 to the first power times 10 to the sixth power, in expanded form, I've got 1 times 10 one time, and then times 10 another 6 times. And I could rewrite that as 10 to the seventh power. I could also look at 5 to the fourth power times 5 to the sixth power. So I've got 1 times 5 4 times, and then times 5 another 6 times, that I can rewrite as 5 to the 10th power. And then also 2 to the 10th power times 2 to the 26th power. So I'm looking at a ton of 2's. But as opposed to rewriting all of that, I could just write it as simple as 2 to the 36th power. So what kind of connections can we make between the expression that we have on the left and the form that we have on the right? And so what you might notice is that the bases in our expressions on the left-hand side all have the same base value. Here I'm looking at 10, 10, 5, and 2, and those bases are the exact same on the right-hand side. I still have a base of 10, base of 10, base of 5, and a base of 2. But how do I get this exponent value from the exponent values in this expression? And you might notice that when I add 2 plus 3, it gives me a value of 5. When I add 1 plus 6, it gives me the 7. 4 plus 6 gives me this value of 10. And 10 plus 26 gives me that value of 36. So instead of having to expand what we see in those expressions, we can simply add the exponents and rewrite this as a single exponent form. Additionally, if we're dividing instead of multiplying, so here we're looking at 10 to the fourth power divided by 10 to the second power, I could rewrite these as 1 times 10 4 times divided by 1 times 10 2 times. And then I could restructure this so that I have a fraction that's going to simplify down to 1, and then that leaves me with these two 10s that I can rewrite as a single exponent of 10 to the second power. Now again, we're looking at these rules so that we can make sense of that weird, crazy function, or expression rather, that I showed you 2 slides ago. So as we continue to look for these patterns, if I had 10 to the sixth power divided by 10 to the first power, so I've got 1 times 10 6 times divided by 1 times 10 once. Again, I'm looking to rewrite it as a fraction that simplifies down to 1. And then that leaves me with 1 times 10 5 times. And I have this single form, 10 to the fifth power. Again, 5 to the sixth power divided by 5 to the third power can be rewritten as 5 to the third power. And then 2 to the 26th power divided by 2 to the 10th power can be rewritten as 2 to the 16th power. So let's think about how this is different from what we saw previously. When we were multiplying our expressions, we added the exponents. But here we're dividing every single time. And so the difference in this case is that when we're dividing these expressions that have the same base, we're subtracting our exponent values. 4 minus 2 gives us 2. 6 minus 1 gives us 5. 6 minus 3 gives us 3. And 26 minus 10 gives us 16. So when you're dividing exponential expressions that have the same base, you're just going to subtract the exponents. So that's 2 parts for us to understand. But what happens if you're subtracting and you end up with an exponent of 0? How do we make sense of that? So I want you to consider this expression 4 to the third power. And I want you to think about how we might describe that verbally. And the words we might use is 1, so that initial value is multiplied by 4, this rate of change, 3 times that exponent value. And so when I expand that, we've got 1 times 4 3 times, and that value is equivalent to 64. Again, if I'm looking at 4 this time to the second power, I might say that 1 is multiplied by 4 2 times. I would expand it as 1 times 4 twice, and that gives us a value of 16. And then if I did the same thing with 4 to the first power, I would say 1 is multiplied by 4 1 time. That's what we see here, and then that value is equal to 4. But before I show you the 0 exponent, I want us to think about some patterns that we might be noticing with the expressions and then the value that we have on the right-hand side. When I'm looking at 4 to the third power, that's equivalent to 64. And when I decrease that exponent by 1, going from 3 to 2, 16 is equal to 64 divided by 4. When I decrease this exponent going from 2 to 1, 16 divided by 4 gives us a value of 4. So when I go from 1 to an exponent of 0, think about what might happen and what this value might be. Because if I'm using this same kind of language, when I'm talking about 4 to the 0 power, what I'm saying is that 1 is multiplied by 4 0 times. And if I'm multiplying 1 by 4 0 times, all we have is 4. And when I divide 4 by 4, we end up with a value of 1, keeping very consistent with the patterns that we've seen. Additionally, if I had 10 to the 0 power, it's the same thing as 1 multiplied by 10 0 times, which is still a value of 1. And I could go as large as 4,000 to the 0 power and still say that 1 is multiplied by 4,000 0 times, and that value is still only going to be 1. So with this, we can make the claim that anything to the 0 power is always going to give us a value of 1 because 1 is not being changed by any kind of rate. But what happens if we subtract these exponents and we end up with something that is negative? So we have this structure here already from the previous slide. And I want you to think about that pattern that we've talked about in terms of division by 4. So 64 divided by 4 gave us 16. 16 divided by 4 gave us 4. 4 divided by 4 gives us 1. What happens when you divide that by 4? So as I continue to decrease my exponent, now I have 4 to the negative first power. If we're holding true to this pattern, what it says then is that I've got to take this 1 and divide that by 4. So what this means is that I'm taking 1 and I'm dividing by 4 one time. So 4 to the negative first power tells us I'm going to divide 1 by 4 one time, giving us this value of 1/4. And then when I go and have 4 to the negative 2 power, again, we're wanting to hold this relationship and keep it consistent. 1 is going to be divided by 4 2 times. And so now I've got 1 divided by 4 twice, and that gives us a value of 1/16. And so we can say that with the positive exponent, it's telling us how many times we're going to multiply our initial value by that rate. When we have a negative exponent, though, instead of multiplying, we're going to divide by the rate that we're given. So let's apply what we had just learned about to this particular expression. So let's make sense as to how this is equal to that 1. Well, when we're looking at like bases and we're multiplying, we know that we can add the exponents together. So here, my exponents for the base of 2 is 3 and 2, so I'm adding those together. My exponents for base 3 is 5 and 2, so I'm adding those together. And I'm going to do that for my numerator and denominator. And that's going to give us 2 to the 5th power times 3 to the 7th, both in our numerator and in our denominator. But now, since we're dividing, I'm going to subtract those exponents. So I have 2 to the 5 minus 5 power, so I'm just subtracting those. I'm going to subtract my 7s. And that's going to leave us with zeros in our exponents. And we just talked about how when we're looking at anything to the 0 power, that leaves us with just 1 because 1 is not being changed by any kind of rate. And so this is how, if you understand these relationships, you can more efficiently compute something like this versus trying to type it into the calculator. But what happens when we don't have numbers to play around with at all? Do these relationships continue to hold, and will they always work if we're looking at an expression like this? You can't really type that into a scientific calculator and find the value, but we can still apply those rules, right? We can still see if this is equal to 1. And when we're looking at multiplying like bases, so I'm looking at x as my like base, I can add the exponents together. 4 plus 1. For y, I would do 6 plus 1, and I'm doing that for my numerator and the denominator. we end up with x to the 5th power times y to the 7th power, both in the numerator and denominator. And again, because now we're dividing, I can subtract them. I would subtract the exponents, just like we did before when we had numbers, and now we're just dealing with variables. But again, anything to the 0 power tells me that I'm not changing 1 by any kind of rate. And so this still simplifies down to 1. So these relationships are going to hold when we're dealing with regular integers or if we're dealing with variables. So just summarizing some of these relationships about exponents, we know that unlike linear relationships where you're looking at a constant additive rate, here with exponential relationships, we're constantly multiplying by some kind of rate of change. And when we're looking at situations that have a positive exponent, that's going to tell us how many times we're multiplying our base. In this example, 3 to the 4th power, it tells me to multiply 1 by 3 4 times. But if I'm looking at a negative exponent, instead of multiplication, we're going to perform division. So here, 5 to the negative 3 power tells me I'm going to take that initial value of 1 and I'm going to divide by 5 3 times. Other relationships that we looked at today, a 0 exponent is always going to result in the value of 1 because I'm not changing that initial value by any kind of rate. 10 to the 0 power says I'm going to multiply 1 by 10 0 times. So it's going to give me 1 as the result. Now when I'm multiplying exponential expressions, for example, 7 to the 2nd power times 7 to the 8th power, and because those bases are the exact same, we're going to add those exponents. We're going to add 2 plus 8, and that's going to give us 7 to the 10th power. And then the last relationship that we talked about is when we're dividing exponential expressions. In this case, 9 to the 5th power divided by 9 to the 2nd power. We're going to subtract those exponent values, and that's going to give us 9 to the 3rd power. So as we continue to think about these particular relationships, looking ahead to next week, I want to summarize kind of the big topics that you've looked at in Algebra 1 for this semester, and then I want to look ahead at some topics that we're going to cover in geometry. So that's all the time that we have for this week. I will see you all next week.